All right. I gotta go back to my screen here. Can you see, am I full screen yet?
Yes.
Okay.
Yes.
I don't know why I can't see it. Why can't I see it? Okay, I can see it. Okay, so thanks for having us here today. And I'm actually pretty excited because I think that there is a lot of grid forming projects being deployed up in Alaska right now that maybe haven't been as widely publicized. So we're glad to have the opportunity to talk about that. First, just in case people aren't familiar, I wanted to just give a little bit of what the landscape of energy delivery looks like, or electric energy delivery looks like in Alaska. There is one sort of grid-connected portion of Alaska there on the right, which is along the road system. It's called the Rail Belt. It's approximately 75% of the population lives on the Rail Belt and has access to grid-connected electricity. Peak load is about 800 megawatts. The remainder of the Alaska population lives in, there's over 200 remote microgrids, ranging the size from tens of kilowatt to 10 megawatt or so. And most of these communities rely on diesel fuel deliveries for their electric power generation. And due to the cost of transporting the diesel, which has to be in, ice-free months only, so it will typically come via barge, and then perhaps, barge to up a river. So it has to be transported and it has to be stored on an annual basis. And so the cost of transporting, storing, and then generating power with the diesel fuel, it can be quite expensive. The actual true costs of generating the electricity can reach $1.50 kilowatt hour. This is actually reduced by state. The state actually has a fund that will actually reduce the power for a majority of the residential customers, but the actual cost to generate is quite expensive. And this extends to heating fuel, which can reach $10 again in places. So that's sort of the lay of the land. So there is great motivation to try to reduce the cost of energy in these remote communities. So does this show up for everybody? Okay, I just need to move my thing. Okay, so I wanted to just give a little bit of a timeline of what's been happening in the state, and it extends quite far back. So I'm using energy storage deployment sort of as a proxy for high contribution renewables, with the exception of the first one, which I'm going to talk about. The highlighted here, I think you can see in red, I've tried to put a legend. So the red is grid forming inverters. And specifically, I know people talk about different categories of grid forming inverters. When we talk grid forming inverters within the context of these remote microgrids, we definitely mean they have to be able to operate standalone. So it's not like grid forming plus or whatever. If you're going to send a grid forming inverter out to a remote microgrid, it better be able to generate the grid all by itself. The blue ones is grid supporting inverters, but notice that almost all of them are being used in sort of a way they're frequency responsive and they're used to regulate and reserve. So this isn't, vanilla connect to a big grid and you just pump whatever power you want. I'll talk a little about the green in a second. Okay, so 1997 was the first time a grid forming inverter was deployed in Alaska, and I don't know if you guys have ever heard Dick Miller speak, but he's spoken about this project before because he was involved in it. It's a community called Metlakatla, and they had a big chipper and the hydro. So they have hydro and a big chipper. The hydro governors were not fast enough to regulate frequency when the chipper load came on, so they would have to run diesel generators, which was expensive, and the generators were not running at full load, so they were just there to provide the oomph that was needed to run the chipper, so it was pretty expensive. So GE deployed a grid-forming inverter with a lead-acid battery. I think I can't really read my own slide. I'm sorry, this slide is not meant for you to see details. But it was like a 1 megawatt, 1,400 kilowatt hour lead-acid battery system, lead acid. And that system actually ran really well. It ran until 2008. They replaced the battery, and then it ran for a number more years. And I think it was actually maybe even within the last 5, maybe 10 years, it was shut down. And actually, that community is going to get a grid connection, if not now, some point soon. So that was the first time, which is somewhat, I think some people find surprising, and Nick Miller has given some great talks on that. And the next two are interesting. So they're in green. So these were non-inverter based grid forming resources, but they were still working towards this goal of to reduce diesel fuel use in these diesel-based microgrids. The holy grail is diesel off, because when you leave a diesel on, you have to run it at a minimum load to prevent wet stacking and prevent health problems with the engine. And this means that you're consuming quite a bit of fuel just to have this engine on, sort of as spinning reserve. So if you can have an asset that can provide that reserve, that is not going to have such a big, not be so expensive at no load, then you can gain a lot of fuel savings. So in 1999, a system called St. Paul, they deployed, this was actually thermal energy storage, and they established grid forming with a synchronous condenser for voltage regulation and an electric boiler, a high-speed dispatchable electric boiler for frequency regulation. In 2002, there's a system called Wales, and this was the first, in the wind diesel system, this was the first energy storage system, was a NiCad battery bank. And grid forming was via a rotary converter. So instead of inverters, we didn't have the GE resources, so there was no access to great development. But so it was a rotary converter, which is a DC machine and an AC machine, coupled to an AC machine, and the DC machine this combination would pump power back and forth between the battery, and that was grid forming. 2015, I'd say, was the first wind diesel system with a true grid forming. First wind diesel system. That's still a correct statement. First wind diesel system with a grid forming battery. This was in Quigillingok, and then followed shortly after in 2018 in Kangeganak. So this was using a grid forming with an ABB PCS 100 grid forming battery, and was a wind diesel system, and was able to go diesel off. That developer, Intelligent Energy Systems, has about a half dozen wind diesel systems right now that are capable of diesel off with a grid forming inverter, and some of those are scattered throughout the red, further down the line. 2019, I'll talk about a little bit more. That's a hydro diesel battery system that got a grid forming battery in 2019, also an ABB PCS 100 that can go diesel off, and I'll talk a little bit more in detail about that. So then there started to get some PV systems. Amy's going to be talking more about this, but these are PV diesel systems with a grid forming battery that can go diesel off. They have an interesting, they were the first, to my knowledge, I'll let Amy correct me if I'm wrong, cases where an IPP is IPP owned. So the PV battery system is owned by an IPP. So that has other interesting aspects associated with it. These next three Bill's going to talk about, these are wind diesel systems that AVEC runs. And they are also capable of diesel off. Grid forming batteries have some other really interesting features that Bill will talk about. And I should have said that across these 200 remote communities, there's maybe like 100 different co-ops that supply power to these communities. AVEC, who Bill and Amy work for, is the largest. They supply power to 58 remote communities, if I'm correct. And then last, so we're looking into the future, and one reason why we are really closely watching the status of the research is that we expect, so in addition to 3 more wind diesel systems that should come online in 2025, AVEC may have more. These are 3 separate ones. With the IRA and BIL funding, if they occur, we should have about 20 more across the strait PV battery systems that are going to have large batteries and able to go diesel off. So there's like this massive deployment that will hopefully still happen in the very near future. Okay, so I was going to say, I'll talk a little bit about this hydro diesel system. Bill has been working closely with their wind diesel, and Amy's been working closely with the PV diesel. So we try to cover all of the technologies. Cordova, Alaska is a community, an off-grid community of about 2,600 in Southeast Alaska. About just under 3 megawatt average load, 9 megawatt peak load. They undergrounded their system a long time ago to improve reliability. So it's a lot of underground distribution and transmission lines. They have a lot of hydro. They have, about 8.5 megawatts of hydro, and then a 10 megawatt diesel plant. In 2019, as part of, with some DOE Office of Electricity Energy Storage funding, as well as part of the DOE Radiance project, they installed a 1 megawatt hour grid forming battery energy storage system. I spoke a lot with Trevor Kudna at CEC, and he explained a little bit about how their system used to operate and how it operates now. So I'll try to show this. So actually, before I show this, their motivation for having this battery energy storage system is that when they can regulate frequency with their hydro, but this requires them to spill energy so that they have up and down regulation. And even worse, during shoulder seasons where there is just enough, hydro to cover the load, they have to run a generator in order to be able to have that regulation capability. And because they don't want to run the generator at low load, they want to run it at, at least at, like, say, 500 kilowatt. They basically have to spill 500 kilowatts of water in order to have to keep the generator at its happy load. So what they've done now with this battery is that they're letting the battery be the ISOC source instead of having the hydro be the ISOC source, and then B, provide the reserve cases. And one thing I think that is important to note in this, in which you may hear in Bill and Amy's talk as well, is that a lot of the research discussions have focused around operation of diesel generators in Droop. But in reality, in most of the microgrids in Alaska, their generators are operated ISOC and ISOC load sharing. And that continues to be the case. Or at least they have at least one asset that is ISOC. So in Cordova CEC's case, depending on the relative amount of load versus hydro, they can be operating, will start in purple in the middle there. When there is, much less hydro, they run their diesel in ISOC. The hydro has two things that can be controlled: the nozzles, which are slower acting, and the deflectors, which can actually regulate frequency. They don't use them to do that right now very often, but they used to. So when they are, when there's not very much water relative to the load, the batteries are off and the diesel's running in ISOC. That's level 2 in the middle. As the hydro starts to pick up or the load starts to drop, they will actually put the battery in ISOC and run the diesel in Droop. And the diesel is then being biased to control the battery state of charge. Hydros, the nozzles in all of these cases are just controlling the level of the water. If as the hydro load continues to go down or hydro goes up, they actually go into this level 0, which is the green, and they'll actually go into cycle charging mode. They'll put the battery in ISOC, diesel's off, and they will run and discharge the batteries till they reach a user-specified set point, and then they'll kick back into level 1 where the diesel's running, and the diesels will run, charge the batteries, and then they'll rinse and repeat, until at some point where they're not in that sort of, equal case, and then they switch either to level 1 or to level -1, which is over there on the right, which is where they actually have excess water power. And now here is they will eventually spill energy, but previously they were spilling energy much of the time. The other thing, here I pointed out that they had some new recent upgrades that were associated with various research projects. And then also part of Radiance, they've installed 6 micro PMUs, so distribution level phasor measurement units at each of the feeders, the battery, and at the hospital. It's a critical load. And so they have been able to start, this is work that they have been collaborating with PNNL for. They've been able to start look at some of the dynamics and interactions between the generators. And this is initial. They're still working on tuning, but they were able to use the micro PMU and come up with some frequency spectrum of what the oscillations look like. And what it has seemed is that maybe at this point there may be a 1 to 2 hertz power oscillation that is introduced when the BESS is in ISOC, and the hydro is also regulating frequency. So just wanted to give a brief overview of this system. And I have one last slide before I transition to Amy, and that is just a little nod to what's going on the rail belt. In this timeline, the shaded gray are rail belt battery energy storage deployments, and so they have not required grid forming in the past. They have been frequency responsive, but they haven't required strictly grid forming. But Golden Valley Electric Association, which is the utility which provides power to all people in all entities in interior Alaska, actually issued an RFP, and they are in negotiations right now with the various vendors, and they are going to be requiring grid forming. And this is going to be a 46 megawatt, 92 megawatt hour battery energy storage system. So that's my only comment on the rail belt, and I'm going to kick it over to Amy.
Thank you, Mari. I'm going to share my slides here. See here. Oh, I see what you mean. It's kind of weird once it starts sharing. Okay. Okay, so I want to give Bill plenty of time to talk. He has some great stuff to cover. So I'm going to go super duper speed through, and we can revisit things later if there's time for questions and discussion. I think Mari did a good job covering kind of the uniqueness of Alaska in the sense that there's so many small islanded microgrids that have, and ABEC has actually been around for over 50 years now doing these types of systems. And so I want to talk a little bit about what we're talking about when we electrically, when we're talking about this microgrid. You might have 3 to 4 diesels, several hundred kW. They're normally staggered in size from each other, which is important for what Bill is covering. And part of the reason for that is because between summer and winter, you can have some big load differences seasonally, and also there's also high imbalances between phases sometimes, even though we do our best to balance. When you're at such a small scale within a small community, it can be difficult to keep all of your phases balanced as well. So my main um, involvement has been on these independent power producer PV and battery grid forming microgrids. And back in 2021, as Mari alluded to, the first of these types of systems went in. And I think if a very good question for you to be asking is, solar in Alaska, how does that work? Well, I think it's really interesting, actually. A lot of these panels are actually bifacial and can absorb the reflections from both the underneath. And in the spring, when you have a lot of snow and the days are becoming longer, that's actually when peak generation occurs. And so here is an example of going diesel off for 7 days of generation. You can see the green is the PV, and um, the red is the diesel, and so and then the yellow is the battery inverter that is kicking in and allowing it's forming the grid whenever the diesels are off, and you can see that purple is a state of charge that's cycling. So the first year that this went in, it was really pretty successful. We had 12% of the energy actually came from the PV, solar. And so that is a really big deal for displacing fuel and saving on cost. The battery also avoided several outages and gave us several hundred hours of diesel off time. However, we haven't been able to achieve similar performance since that first year because we realized that our diesels were getting overcooled during this time. And so there's a lot of heat issues that we're still working our way through right now. And but that's in terms of, what are these projects actually doing? What are some of the results that we're seeing? I just want to highlight, what can be possible. And I also want to touch on some of the stuff that Bill has been involved with wind and battery. We have two communities, Stebbins and St. Michael, that are intertied to each other. It had a 900 kW wind turbine and 720 kW grid forming inverter bank that went in. And um, just in 2024, we were able to see 43% of the energy production that Bill's system controller operates was wind versus what would have been a lot of diesel fuel. So we're really excited to be seeing the fuel savings from that sort of project. And from a practical standpoint, my goal is to convey, well, what are the things that nobody told us about when we started actually doing these projects and having the rubber hit the road? So one of those things is that the battery cells are actually really heavy. And so considering, logistics, especially when we're talking about such remote areas that don't, you don't have a forklift down the roads aren't paved, there's a lot of logistics that are difficult in these communities. So just thinking through that, including there was a lot of shipping material that was actually left over from packaging and shipping all of the battery cells. We had 5 pallets of styrofoam that were like, what do we do with now? Are we backhauling this? Are we storing this? And then also just, part of the appeal of these battery systems is that you're getting away from diesels that have moving parts and have a lot of maintenance. But the reality is you can't necessarily get away from operations of having a coolant leak, which, has happened as well. And then from electrical operation, just again, spouting off really quickly what, you know, oversizing your inverters and sizing it for winter peak load to be able to avoid outages in the wintertime, even though with PV, summer is the peak PV generation season, you still want that battery to act as your source of redundancy. Um, Another thing that we had expected to do was to switch between grid forming and grid following. Whenever the diesels were on, we expected to run in grid following, but when it came time to do that, there were some communication latencies and was instability and flicker, and it didn't actually work very well. So we actually run in grid forming mode all the time. And I know some others that I've talked to do operate switching back and forth, but to do that successfully, they have hardwired contacts to capture those transitions and avoid the latency issues over doing that over communications. And then another surprise was just how equalization for these systems translated to downtime. Um, we weren't really expecting just the frequency and duration that was required to keep all of the cells balanced charged with each other. And um, bring this up because of the, UNIFI is focused on, we did find that now that we've done a handful of these systems, there's a lot of variation between inverter manufacturers. Some of the set point types that govern, synthetic inertia and droop, there's a lot of variability from one to the next, and it's not always really well documented from an application in user end side of things. And so, we find ourselves really having to rely pretty heavily on manufacturers for getting all of those knobs dialed in on a new system and being able to tweak them over the first year of service. An engaged integrator is absolutely critical. Again, I'm trying to speed through this real quick. One specific example that I want to give of a set point that was changed according to a manufacturer recommendation is because we had way more current on a bank of paralleled grid forming inverters than we expected. And there was basically a lot of circulating currents going around. So I'm just going to skip to this. We call it dithering, but essentially you can see on the left where all of these devices were kind of fighting each other. And then once the right set point change was made, the KW smoothed out significantly. They were no longer fighting each other, and we actually saw 50% of the amount of current on that same system of inverters, cutting that in half. And the reason why that's important is because we also weren't really prepared for how much heat actually comes off of these, and being able to remove that heat from the module. We had to go back and add a split unit air conditioner, and that was able to help keep up with the need for cooling and ventilation. We still have a lot of challenges in terms of being able to keep the power plants warm and figuring out how to size. It's a complete paradigm shift to go from these diesel power plants that always have way too much heat that you're trying to get rid of. And now all of a sudden we're turning the diesels off and we're trying to keep these power plants that aren't really well insulated and enclosed because, just get rid of the heat. Now we're trying to hold on to it. So that's a big transition that we're also getting used to. And finally, I think we've had some issues on some of the systems, specifically the PV BESS projects that are done through an independent power producer. And we've seen some reactive power imbalances affecting our diesels, and that has become really difficult to troubleshoot. So we're left wondering, um, how can we front load this with rigorous factory testing with a reactive load bank, and being able to really get some baselines established, because once you get it installed in the field and you have these variable loads and they're, feeding customers and it's really remote, it's very difficult to go back and troubleshoot these systems. And so how can we sort of be ahead of that in future projects? Here's an example of going back from diesel off to diesel on. There was, it's really a pretty slow time scale. You can see that over, um, you know, 45 seconds to a minute or so. The kVAR on the diesel actually goes down to negative 190 before it brings itself back up to 80 kVAR, which is the normal operation. And so, trying to untangle between an IPP's equipment and ours, what are the underlying issues? Why are we having these power swings? How can we address those to be able to take full advantage of these resources that are installed, instead of having to do curtailment or limit our batteries? So we're still trying to get the best degree of operation out of these projects. And I look forward to discussing that further. And I would like to hand this over to Bill.
Thank you, Amy. I thought that was great. It fills in some of the gaps that are in my presentation. I have to give a warning here. My presentation is geared towards inverter designers, developers, and systems integrators. It's really a large offload of issues from the end user. I want people to understand where we're coming from, why are we going and installing all this shiny equipment in the middle of nowhere, Alaska, and then what our requirements are from the inverter suppliers. So not much time, so we're going to cover a lot of ground. I apologize for being very fast. I'm going to be faster than Amy even. So let's see if I can find it. Okay, is that all working?
Yep, it looks great.
Okay, great. So what we're after here is to get the maximum benefit of renewables and to save fuel. So there's two sides of the same coin. We're trying to reduce fuel, of course, but we're also trying to get, when we install renewables, we're trying to get the maximum benefit of that. We have found that installing large turbines and having a great deal of excess generation, be it PV or wind, is the way to go, because it's once you commit to putting a wind turbine in, for instance, going bigger is a marginal cost, but it does give you a much higher degree of diesel offset. And then what do you do with all the excess electricity? Well, that's where beneficial electrification comes in. It all ties together. It's very complicated to do in the middle of nowhere, Alaska. I don't know why I'm such a masochist to even try this, but this is what we're doing. My talk is broken into 3 sections. The first thing is, why are we doing this? I think that's really important for the vendors of this equipment to understand. Why would we even buy it from you? Well, because we expect these benefits. The second one is, we have a set of requirements that have been hard won from our issues that we've had up till now trying to install, especially GFM inverters. And finally, we have a new challenge here. I haven't seen anyone that's prepared to control these microgrids to my satisfaction, so we have been supplying our own system controllers. It's a lot of work, and we're looking forward to actually having vendors that can properly commodify the supply of system controllers. I'm not doing this for fun. So AVEC is microgrids. Remember that. So this is, our typical sort of setup here. We have multiple diesel generators. They're all controlled by a diesel dispatch controller. We are also installing. We looked at ultracapacitors. They're still in play for various reasons, but batteries, basically an inverter, filter, feeding in on the in this case on the AC side. But we also connect them directly to the power plant bus, and then we have a wide variety of loads, commercial loads, residential loads. They put their own solar systems in, solar panels in. We have wind generation that's out where the wind is good, so it's out in the distribution system somewhere. And then we're installing these utility solar farms, either ourselves or our IPPs. So the point here is, it's getting complicated. AVEC is microgrids. As you've heard, 58 rural communities, 50 power plants, 13 wind diesel systems. They serve 19 communities, and so far we have 3 wind diesel battery systems, but we've got a lot more coming. They're up for grabs, guys. So if you supply them, we would like to discuss this with you. And we want to avoid the pitfalls that we've fallen into. Look at the 1,000 miles. These things are in the middle of nowhere. The logistics of supplying the equipment and getting installed is incredibly difficult. Put in a container, but we still have to get it offloaded from the barge. We get it on the shoreline, and so we've got cranes, we got front end loaders. This is the heavy equipment that we have to work with. So we're vitally concerned about the weight of the batteries. Maybe the batteries have to be broken up into different a number of containers, that sort of thing. This is bushwork. Okay, now here are the reasons. Stability is very important to us. We have situations where we've had to curtail the generation of our wind turbines simply because the engines cannot handle the wind variations. This is nothing, that's not the fault of the wind turbine itself. It's just simply that wind is up and down all the time. It's like riding a bucking bronco. And that has 2 sides to it. One is that not only does the customer take the brunt of poor quality power, not only do the diesels lose efficiency by ramping up and down all the time, but even we have trouble keeping the turbines online because they were all tested on a nice grid system, and then we go and put them out in the middle of nowhere, Alaska, and expect them to operate. So having a solid power system helps everybody and improves the ability of these wind turbines, for instance, to successfully generate. Spinning reserve. This is the #1 benefit stream. If we don't have this, when we put wind turbines in, they tend to be so unreliable not just because the turbines will trip because of poor quality power, because of being a new bleeding edge technology, but also because the wind is going up and down all the time. So we can't trust them. We can't trust them very much. I usually dial in about 20% trust on wind turbine output. So we need to have spinning reserve. And what we do right now is we end up, if we've got a big wind turbine there generating, we end up with a big diesel also running at very low power, because you don't need the power because the diesel's running. Because the power is being delivered by the renewable, but you have to have a large diesel that's lightly loaded. And that's harder than diesel. It's wasteful. The large diesel burns off a lot of fuel, and it's very inefficient. So right off the bat, just having 10 minutes of reserve bridging power gives us that ability to hugely increase the efficiency of our systems. Improves reliability. If we lose that wind turbine, we lose a diesel even, then we want a source of bridging power, which is why we need the GFM in order to keep the lights on while we bring up another solar diesel generator. Note that this is minutes only. We only need minutes worth of energy storage in order to get that major goal accomplished. We need to prevent too low diesel loading events. I will show you the fuel curves in just a minute, and they show you that we don't want to run the diesels too low. If we don't start to run them too low, it's bad for the diesel, even worse for the diesel, and it's very inefficient. And this is where we can use the batteries to keep their loading up. The inverse is also true. When you get them highly loaded, it's bad for the diesel. They can get overloaded. You can burn the diesel out if you let it self-sacrifice itself trying to keep the lights on. The idea is to generate some power to assist it using the batteries. So now, just a quick look at fuel curves. These are two diesel engines that we commonly use in a lot of villages. They run at different speeds. Just a couple of things I want you to note, and that is this. First of all, the top two lines are how many kilowatt hours can you get out of a gallon of diesel fuel? And you can see that if you're above about 100 kW on these two engines, 75, 100, you can keep the efficiencies fairly high. However, below that, they drop off like a rock. And the main reason for that precipitous drop at low power is because it takes fuel just to spin the engine. And if you look at the two bottom curves, you can see that because they're basically straight lines, more or less, but they intercede the y-axis. For the 1800 RPM generator, you have to burn 2.5 gallons of diesel fuel an hour just to spin that, even if it's not generating any power. And that is why those kilowatt hours per gallon numbers, the top two lines, drop like a rock at the bottom. So the point is, we want to avoid running in the bottom end. We want to avoid running in the top end. Note that efficiency is okay, but what we're doing there is possibly burning out the engines. They're just overloaded, and we have to avoid that. So two different situations at each end. In the middle, do we want to mess with the diesels? No. I want to run the diesels. They've been developed for over 100 years. They know what they're doing, and they can do it fairly efficiently. If you have to run a diesel, let it do its job in the mid-range, but look after it at the low and the high ends. And this is something that is so hard to get through to the vendors up to this point. So I've talked about the 8 reasons that we want to do GFM inverters. Here are our requirements, and these are from painful lessons that we've learned. First of all, we do actually ask that they be GFM. We don't want a GFL inverter. We want 4-wire connections. We want to be able to connect them to our power plants potentially, and our power plants are 4-wire 40-volt Y systems. So your inverter system should be capable of 4-wire neutral supported 40-volt connection. If you don't do that, then you're going to tell me that you're going to install a transformer to do that. So my third requirement is no isolation transformers. I don't want a transformer that is being installed simply to match voltages or supply a neutral or provide isolation. I will go to the inverter vendor down the street that does not need that because of the expense, the lead times, and losses associated with transformers. So here's the Stebbins BESS system, 720 kW. It's quite packed in tightly. You can see that the access to the battery racks is from outside, opening the doors. I'm not sure if we would want to do that again. It's so far it's not been a problem, but obviously if you're in the middle of winter and it's snowing, this is not something that's optimum, having to go in through the outside. So carrying on with our requests. Faster balancing and equalizing of batteries. I do not want to waste any more time than necessary equalizing batteries. I need it to be done at a reasonably high rate, and I'll be looking at the comparative equalization rates that are estimated. And there may be a penalty involved with that. If you take too long to equalize the battery, I am losing service while you're doing that. Also, I want the balancing circuits to be running continuously. You should be logging which cells have a high self-discharge rate, and you discover that when you fully charge the bank and you equalize all the batteries up to the same voltage of charge. But you remember which ones needed the most balancing. So you remember that, and you give them a balancing charge even when they're operating. So I don't have to deal with it by taking the whole battery bank out for a day or two. In the balancing circuits I've seen right now, they're typically 1 amp of balancing current, and that's pitiful. On a 500 amp hour battery, do the math. That's 500 hours, if you had to charge it from dead bottom to dead top, most of a month. Of course, that doesn't happen, but we have a disconnect going on here. Adjustable inertia. We need settings. Amy referred to this a little bit. We need a nice, clean, simple way to adjust inertia. To go along with that, we need adjustable dampening. We need a clean, simple, well-documented way to adjust the dampening to go with the inertia. And then, of course, because it's a GFM inverter, we're going to talk about Hertz droop and voltage droop. And then, of course, once you have these droop settings rolled in, and to the extent that we want them, to the extent of droop that we want for best operation, which is typically we've used a half a hertz, and we use 1 hertz, it seems to work. Then we want to be able to send set points to it, and that would be through communications. And it's been working fine for us. If we get these controls and set points and droop, it seems to work well. So just a quick look at battery technology. So these are 10 cell racks, modules, and you can see inside there's 10 cells, 500 amp hour cells. And the reason I'm showing that is look on the right there. That's a balancing circuit board. It's got 1 amp resistors. They're size 3 ohms. They put a 1 amp load on each battery, and that is what they use to balance off the batteries. They turn the batteries that are already fully charged. They throw on the 1 amp resistor to keep them from charging up anymore. Meanwhile, the batteries that are not fully charged are left with the charging current until everyone's balanced off nicely. And only then do we get to actually run the battery bank. That's got to change. It's got to be done smarter. Adjustable voltage droop, frequency set point, and then for voltage set point for VAR and voltage control. Amy's been having trouble. I have not been having trouble because I've got a system controller that takes charge of this all the time, and I do not switch from GFM to GFL. We stay on GFM, and we don't. So far, I've not had any transition issues with going diesels off to on. Fingers crossed. We want a standardized control interface. Right now, we want to use Ethernet, and the protocol that we're currently using is Modbus over TCP. We're not asking for a lot, but we do not want any kind of proprietary communications protocols. They have to be something standard so that we can replace our equipment in the future. Arrays of inverters. We love arrays of inverters. We've used Oztex. They seem to work fine. Amy mentioned some of the issues with having a large array of inverters, and I've mentioned that. Arrays of inverters are very appealing to us because they're easier to pull out and replace, but they got to work. and they got to work reasonably efficiently. I've already mentioned power plant connectivity. They've got to connect directly up. How are we doing for time? And factory acceptance testing, Amy also mentioned that. We've been caught short, and we're not going to allow that to happen again. When we get a GFM inverter, it better be factory tested, or there's going to be problems. And we need to see a certified or a witness factory acceptance testing done on GFM inverters, because up till now, people have been playing games with us. Of course, whoever's listening to this will not be playing games with us, but that's because people are learning very quickly about how to do GFM inverters. But there's been a learning curve over the last 5 years, and it used to be that only certain vendors were able to provide the gold standard of a GFM inverter that you could expect to work. Now it seems that there's quite a few, but we're still filing off the rough edges. So we do want the inverter capacity to be able to carry our peak system load. So, and that's done so that we don't have to worry, and that no matter what is going on, the wind drops off, the diesels we lose the diesel engines, that we can still keep the lights on. Battery capacity, I've mentioned this before. The standard seems to be 1 hour batteries, and we'll buy a 1 hour battery if that's the best economic solution that supports the inverter capacity. We want that inverter capacity. In item 15, we will buy a 1 hour battery if that's all you've got. We've looked at lithium titanate batteries, so we can do that with say a 6-minute battery or a 10-minute battery. That appeals to us because the battery rack is much smaller. The cost did not appeal to us. Ultracapacitors, the same thing, except even worse. We'd love to have ultracapacitors because they're easy to service. We can discharge them, then we can go in there and do our work, and then recharge them. The equalization is a little easier. So parasitic losses, we're going to be asking a lot more detailed questions about how much you're going to lose in operating your system. And it's not just the IGBTs being 98% efficient. We want to know how much power is being lost in the inductors, the capacitors, the HVAC in the unit, everything. We have to add this all up, because if you install a GFM inverter and it takes 5 kilowatts to run it, that's going to cost us practically $250,000 before we're ready to retire this thing. It has to be factored in. Also, we have inverters out there that if you hit their rated output, they give you half a second, then they trip. And that is not acceptable. What we really want is the thing to droop off to warn us that we're overloading the thing, but give us a chance to shut down frequency sensitive feeders, for instance. And then we can talk about trying to figure out why we're getting overload. Meanwhile, we're not having a precipitous loss of generation capacity, which we always try to avoid. This is generation 101. I threw this up because just to remind us of what the various technologies are. Can you see my cursor? Look at this gap in here. This is basically where we're at. We don't really need the energy density of a lithium battery, but we want to push it over to the power density of an ultracapacitor or a conventional capacitor. We're in this gap here of what our usage cases are. And so just something to make a note of. And you've probably all seen this stuff, but battery racks in the center, there's the inverter array. If you zero in on that, you can see that they're Oztec inverters. You're using a lot of them. We're buying more of them. On the right, ultracapacitors. In case you have never seen an ultracapacitor rack, there's one for you. And that's it for my main talk, Murray. How am I doing for time?
I think you're okay. Go right on ahead.
Okay, so the third part of my talk is the next challenge. So AMEC is doing its own system controllers, because I have not been happy with anything I've seen out there, because they don't handle everything I've asked for in the first part of this thing. I said we have 8 benefit streams. I want to handle them all. I want to get the maximum benefit of putting a battery in by reducing the servicing on the diesel. So we have certain requirements to minimize the servicing on diesels and take advantage of that benefit stream. These things all add up, and we could certainly justify buying a whole slew of BESS systems if we can simply pay attention to the details. So I need a system controller that does all that. So I'm willing to talk to anyone that says they can do it. We expect the GFM inverter control is going to be sorted out, if not already, within the next few years. Everyone's going to be doing it. It's going to be standard stuff. We all know the algorithms that are required. We know the coding that's involved, and there'll probably be a few really good suppliers of these things that do a lot of sales, simply because they can hit the marks that I've given earlier in this talk. However, the routine expertise regarding how to handle everything, it's very difficult because you've got a lot of competing priorities here. Do I charge the battery? Do I run the diesel a little harder? Is the diesel going to get underloaded, overloaded? What's wind going to do in the next 5 minutes? It's always going to be changing. And when really can I go diesels off, truly, without putting an onus on the batteries to make up the slack, and hence I'm using the battery longevity. The biggest problem I've got right now is I don't have a good estimate of the cost of running batteries. I can't do it in kilowatt hours. I cannot do it in kilowatts. What I'd love is a longevity meter on the front of the battery rack that tells me it's 100%, then keeps dropping every few percent. I look to see how many percent it drops every day. I'll say, oh, we're using the batteries too much. Okay, let's dial this one back. But right now I'm guessing. My tendency is to go as easy on the batteries as possible, but still get the benefit streams that we've talked about. So do we need this? May require AI. I hate AI though, because I like predictive algorithms, and AI is not a predictive algorithm. So you guys figure it out and then come to my doorstep, please. What we actually do is, you got to remember where we come from. We come from using diesel engines, diesel power plants, and taking a very great deal of responsibility for keeping the lights on. We've got our subscribers out sitting in a dark house with in the middle of winter, and it's not going to get light until February, and the wind is blowing at 40 miles an hour, and it's minus 40 degrees. They would like to have electricity, please. And I do not want to say, well, we've installed all this shiny new stuff. I'm sorry, there's something wrong with the software. So, we'll fix it real soon now. Meanwhile, they're shivering. This is not acceptable. So what we've got are control systems that work with the diesels. They provide isochronous high quality power as long as the diesels are running, and they look after switching engines, and they've got various stuff in there, but no inverters. So when the renewables are added, when the inverters are added, all the fancy shiny stuff that's supposed to be the way to the future, we want them to be added to the diesel plant. We do not want them to take over the diesel plant. And I've had vendors say, well, we'll install a system controller for you, and we'll run your diesels, and we'll run the renewables, we'll run the battery. And we just say, it's a non-starter. We don't want you anywhere near our diesel plants, and that's never going to change. So remember that. And you can read, I'm not going to read this out right now because there's so many details in how the diesel dispatcher has to operate, how many responsibilities it's got. There's a long list here, and they'll post this, and you can have a look at it. But remember, we do not want anyone coming in to try to do this for us. There's only one number that the diesel dispatcher needs, and that is how much spinning reserve are you supplying somewhere else that I'm not aware of, me being the diesel dispatcher, and also how much village load am I not saving because you're supplying it with a renewable? I need to know that as well, so that I know what the whole picture is, and I can maybe shut down a diesel because I don't need it for capacity, or maybe I have to, and that would be our goal, to shut down the diesels, at least go to a small diesel or to go to no diesel. So. The system controller has a whole bunch of requirements. read this. If you're going to talk to me about a system controller, make sure you read this. And I'm not going to go through it right now, but there's 3 pages on system controller responsibilities. See if you can get all those marks. Finally, beneficial electrification. I started this talk by talking about beneficial electrification. Well, what's required to actually make that happen? This is how we're doing it. And you can read this later too if you want. But remember, if you put beneficial electrification in and you try to sell electricity at a lower rate, there's several things you have to do. And one is that you have to secure that so that a guy just can't move his load and jumper out the control system. You have to meter it so you know how much low tariff load is being used. So you don't have to rewire the whole house and put it on a separate utility meter, which is a non-starter for me. It's just too expensive and too much trouble and clumsy. Instead, what I want is a box that monitors how much you're using at the low tariff rate and then communicates back. It's got to talk to my server to find out if there's actually low tariff energy available. And then when it uses it, it's got to communicate back how much it's using. And by the way, if you do use the power when there is no excess available, then you're still going to get the power, but you're going to pay the higher rate for it. And there's going to be a little light on that box that says, hey, you're being warned. This is high cost power you're using. Okay, so that's about it. Did we get through it?
Perfect. Thank you, Bill. So everyone.